I'm very pleased to welcome today's keynote speaker, Dr. Linda Lee. Dr. Lee is a professor in the Department of Agronomy at Purdue University. She is also the program head for the Ecological Sciences and Engineering Interdisciplinary Graduate Program and is a courtesy faculty in the Environmental Ecological Engineering. She earned her bachelor's degree in chemistry and a master's degree in environmental engineering and a PhD in soil chemistry and contaminants hydrology from the University of Florida. Dr. Lee's group researches environmental fate processes and contaminant remediation in various medias for use in mitigation, contamination, and management decision tools for industrial and agricultural settings. Her research over the past 15 years has focused on per and polyfluoroalkyl substances, otherwise known as PFAS, and organic endocrine disrupting chemicals of emerging concern. So Dr. Lee, thank you so much for joining us, and allow me to stop sharing so that you can start presenting.
Thank you very much for inviting me to give this talk today. And I'm going to focus on really the challenges that we have in waste management because of PFAS. So I'll do a few basics, but you already heard several talks yesterday that talked about PFAS, so we won't spend too much time there. And then I'll focus on PFAS in waste-based amendments. We'll look at guidance levels a little bit and some treatment technologies, and then some perspective and path forward. So what are PFAS, per and polyfluoroalkyl substances? Depending on what is the latest reference you've read, we have up to 5,000 or maybe over 7,000 of these different substances that have been produced and possibly in our commercial products. And you have likely seen this paper before, but I like how it just shows that this is a family of substances. Everything has a perfluoroalkyl chain length that can be of varying length. Okay, so within each one of these subclasses, we have unique differentiating characteristics, the carboxylic acids that you're probably very familiar with, the sulfonic acids, and then several other different substituents that make that particular group of PFAS its own subclass. And then each one, as we've said, has a perfluoroalkyl chain length and can have different chain lengths. So within every subclass, you have multiple chain lengths. And then for some PFAS, you have multiple isomers. Perfluorooctane sulfonate, so PFOS, that you're probably also very familiar with, has numerous isomers, not just the linear one. And so we have to deal with that. There's, it's not uncommon to have at least 6 or more isomers in a waste matrix. What's also unique about these from a lot of the compounds we've had to deal with in the past is this class or family, they don't degrade, or if they degrade, they just degrade to more PFAS. And so, yes, there's biotransformation, but it's just to other other PFAS. So I have 2 examples here. On the left is a telomere example, that ethyl group in between the perfluoro chain and the alcohol group. That's the key feature of a telomere-based PFAS. And then you see the electrochemical one on the right. The SO2 group in the production process is in the electrochemical process is a key feature for those PFAS. But both of them, both groups of PFASs degrade through multiple steps and multiple pathways, and so create a variety of intermediates. And when we talk about precursors, we're usually talking about PFAS that end up, can be transformed to the final terminal products. But there's several intermediate PFAS. You have a kind of a parent PFAS, several intermediates. 2 of those are now on the EPA list that they are now trying to optimize methods for. And then these intermediates eventually go to these persistent perfluoroalkyl acids. For example, A2 telomere alcohol will primarily go to PFOA that you're very familiar with, but it also will go to other acids. And then the sulfonic acid PFOS will be generated from our electrochemical derived PFAS. And together we call all these the perfluoroalkyl acids, these terminal metabolites from microbial degradation. And so I want to highlight another thing about this, and that's that there's different rate limiting steps in the pathway. So here again, I have two different molecules I'm showing you, precursors, and they can degrade. One goes directly to telomere alcohols before it then goes through the multiple steps and pathways to become the terminal metabolites, the perfluoroalkyl acids. The one on the right first will degrade to fluorotelomere sulfonate, which we see showing up in a lot of our waste matrices. And that's a relatively fast process compared to then the next process, which is to get it to a telomere alcohol. Once it's this alcohol, it can degrade really very quickly through multiple steps and pathways to our terminal metabolites. So this is important because when we're looking at wastewater and biosolids management, we have PFAS from multiple sources coming into our wastewater influent, and those sources, depending on what they are, will contain, might contain more of some type of PFAS than others, might just contain a whole range of them. And then in our wastewater treatment process, we have various types of processes that are happening and different treatment stages depending on the plant that you're looking at. And the PFAS are either going to sorb to the sludge or they're going to be discharged into the effluent, either how they came in or transformed in the process, as I've already highlighted. And then whatever's on the sludge might be converted to biosolids. In the United States, we land apply for beneficial reuse over half of the biosolids that are created from our water resource recovery facilities. And what we find out, and this has been known for quite some time now, is that the things that you quantify in the influent, which is a very small subset of PFAS, end up being higher in the effluent than's being discharged or higher in the biosolids because of that biotransformation process we just discussed. And then eventually for beneficial reuse, these biosolids will be land applied on as a soil amendment and undergo additional aerobic degradation processes that are common for that environment. So unfortunately, the challenging truth is that all of our current practices just take PFAS that are coming in and create, either don't change them or change them to different PFAS coming out. And the fluorine mole balance hasn't changed, but the number of PFAS we quantify goes way up because the subset we quantify tends to be more of the intermediates or terminal metabolites. And these production practices I already mentioned will vary between aerobic and anaerobic, and I'm going to highlight an example for that. And then biosolid properties vary. I wanted to mention that a lot of people, when they talk about biosolids or think about them, just think about these nice little solids, but actually they vary from very dilute slurries, dilute in terms of solids content, such that those would be subsurface injected or sprayed onto a field, all the way to pellets that get sold, that are oftentimes the most common ones sold commercially in Home Depot and Walmart. So you have everything in between. Then they can vary in their aluminum and iron content because of what's used in the stabilization process. They can vary in pH and ionic composition, organic matter content, and then protein content is something that has been recently looked at because we know PFAS like to bind to proteins. And so there's just a lot of things that vary in our biosolids. So here's the example I want to show you of anaerobic versus aerobic process. So here's a typical, these are biosolids that were created in a relatively typical anaerobic treatment process. And you can see, first of all, the big thing that what we measured pre, and all the legend down here shows what was measured. So it was the perfluoroalkyl acids, several intermediates, and we eventually did measure precursors in these. So you have much more showing up in the post. It's not that fluorine mole balance has changed, it's just that what we quantify has increased. And overall, the terminal metabolites increased by a factor of about 2.5. And then the known microbial metabolites that we tend to look for, 7,3 and 5,3 fluorotelomere carboxylic acids, they went way up. Remember I told you fluorotelomere sulfonate, it's an intermediate precursor. Well, there was a lot initially and those decreased in the process. And then it's important to realize that you could get, even if something's not changed at all, you will see a concentration increase because you actually have solids mass reduction during the treatment process. Here's another example. This one is an aerobic example, specifically an autothermal aerobic digestion process that they use up in the Chicago area at one of the plants. And again, you see that, post is greater than pre for what's going in due to precursor breakdown. And what we also, and so here's a little more detail, and you should have seen this if you got to join the lightning talk by Caroline Lucal yesterday. We see a huge increase in the carboxylic acids. I showed you 2 degradation pathways, one to the carboxylic acids and one to the sulfonic acids. The carboxylic acids degradation pathway from fluorotelomeres, those create a lot more acids than the sulfonic acids that are created from our electrochemical derived PFAS. And so it's not surprising to see a lot more generation of the acids and more of the shorter chain versus longer. That also is controlled by the precursors present, whether they're long chain precursors or short chain. And then much less of the sulfonic acids, because the degradation pathway to the sulfonic acids tends to be less efficient. So your yield is much lower than the carboxylic acid pathway from the telomere derived compounds. And also you tend to only create the one sulfonic acid that was the chain length that of interest, where the carboxylic acid, you can create several. So we see a lot more transformation happen in the aerobic process versus anaerobic. So what you quantify in the end biosolid will look higher. Mind you, whatever you don't degrade in that process will happen once it's land applied. So I'm going to show you some data for, I should have maybe showed you this general analytical approach to begin with. So, we extract the solids usually with ammonium hydroxide methanol extract. We add internal standards, so isotope labeled PFAS. And initially we were just looking at the terminal products, but subsequent work, we started to look at up to 60 different PFAS compounds. That's about all the standards that are available. So you're kind of constrained in terms of accurate quantitation to that. We can look for precursors different ways. You've probably heard of the total oxidizable precursor assay. Didn't get to hear all the talks yesterday, so don't know if it was mentioned. I know Piggy was mentioned, but that's not a standard procedure. It's much harder. You have to have special equipment for that. The top you don't. And then we happen to have the capability, because we have a QTOF, of being able to do suspect and non-target screening of other PFAS. And then we like to evaluate, well, if the PFAS is present, how much can actually be released to the pore water if it was land applied. So I'm going to show you some data here for 3 different types of soil amendments. We have at the top the municipal waste compost. Those are derived from city waste, not biosolids, but tree trimmings and compostable organic materials. So packaging and anything that is compostable can be mixed into this type of waste that is created in our households. And the middle group are soil amendments that are not biosolid based. And then you have your biosolid based on the last panel. And so what you'll see here clearly that there are overall higher loads, and these were only alkyl acids in this study. In the biosolid based products, ranged from 30 to close to 200 ppb. You see that mostly the long chain present in the biosolid products, where in the municipal waste compost, they were shorter chain. And so we questioned whether that was because of year, because the biosolid based products were collected a few years prior to the waste, the municipal waste composts. And then you'll also notice that in the municipal waste compost, the ones that all contained a lot of compostable food serviceware, so basically food packaging, paper plates, they had much higher loads than just looking at grass or somebody's backyard compost. And I always get asked, well, what's in, where did PFAS come from in that backyard compost? Well, they did have some food waste in their coffee grounds and unbleached coffee filters, but honestly, we have PFAS atmospheric deposition, depending on where you live at different times of the year. You can have PFAS just naturally to be deposited through rain events. We have insecticides that either have it as a primary ingredient or as an active ingredient, as an inert ingredient, as a surfactant carrier, or it can be present in the bottles that hold the pesticides and then they leach into the pesticides. And then you can have contaminated groundwater that you might be using for irrigation. So then if we looked, at that time, we were only doing the acids. So we were using the top assay quite a bit then. And what the top assay is, I'm going to show you a little bit more on the next slide. But basically, it's a high pH per sulfate, high temperature oxidation process that will convert the precursors, not completely efficiently, but convert them to carboxylic acids. And so here what you're seeing is a series of commercially available biosolids and the amount of perfluoroalkyl acids that were in actually just the carboxylic acids, the solid bullet, the solid bar, and then the open bar is how much more we saw when we did the top assay. And so that indicates to us there's a lot of precursors present that might lead to these terminal metabolites that have not been quantified. And just for those of you that this is a relatively new assay to you, the top assay is designed to convert all precursors to these carboxylic acids. So a little different than what would happen from a microbial transformation process. As I mentioned, the conversion efficiency varies. So here's an example of 3 electrochemically derived PFAS. They all degrade pretty efficiently to a single carboxylic acid, the one that matches the carbon chain length of the perfluorocarbon chain that was on these. And these all had 8 perfluorocarbons, and then that converted to PFOA. Contrary to that, you have your fluorotelomers, and they break up to usually about 4 with a couple that are primary acids. And that is, similar to what happens in microbial degradation. You don't just get one carboxylic acid. So here you see you get several. And in some of these cases, the efficiency is not as good. It just depends. Different compounds have different efficiency. Now, these were all done single compound. So once you have a mixture and you have a complex matrix, things get even more complicated. But it does, so it needs a lot of investigation and optimization for labs to use this commercially, although some are offering it now. But it still is a way to explore, I say, precursor abundance. It doesn't account for precursors that were extracted, and you'll hear me say that a few times. There are a lot of side chain polymers that are not extracted at all in typical extraction processes. And then at that time, since we were only doing those acids, we did suspect screening later on these, and we saw that there was a lot of the sulfonamide containing PFAS, fluorotelomere sulfonate, and a lot of the phosphate-based PFAS that were present both in the municipal waste that did not have biosolids, as well as in the biosolids. So then you want to think, well, they're present in the biosolid, how much will actually be released to pore water? And I actually had a hypothesis that a lot of it would not be released and it would vary with biosolids. Well, so we do these little pore assays where we put our biosolids in a syringe, saturate it, and let it sit for 24 hours. We checked, usually with sodium azide to minimize degradation from precursor to the acids. And here I'm showing you pore water concentration on the y-axis as a function of the concentration of the perfluoroalkyl acid in the actual product. And you can see basically as the product concentrations increase, we see increase in the pore water. So it seemed to be more driven by actually what's in the product. And I'm going to show you how we correlated that and normalized that in a minute. And I just want to remind people, yes, these are in very high parts per trillion, but this is just what's in the pore water immediately next to the biosolid. Biosolids are usually mixed at a 1 to 3% with soil. So we're going to have a lot of dilution and attenuation. So don't get too worked up about that. But you see, we saw very similar trends between both the biosolid-based materials and the city waste, which was just composted paper packaging and leaves and tree trimmings from the city. And then I mentioned biosolid properties can vary. And so we wondered how these properties might impact PFAS release. And I don't have time to talk about all the potential impacts. I will just show you what we saw very strong correlations with. So if we normalized, if we took what was left in the biosolid relative to what was in the pore water, so essentially a partition coefficient, normalized it to organic carbon, we saw a very nice trend with fluorinated carbon chain length. And we saw similar for the biosolid-based products as we did for the municipal solid wastes. And we saw what appeared to be a different trend between the sulfonic and the carboxylic acid, not unusual, just a slightly different, but we only had 3 sulfonic acids. So that kind of limited that, really tweaking that out. And so we saw this very strong correlation. And that actually meant that if I knew the PFAS load in the biosolid and the carbon content in the biosolid, I could predict what would be released in the pore water. Interestingly, KOC concept has not proven to be a generally universal term for PFAS in the soil water environment for a lot of reasons, because there are a lot of, in biosolids, you have a lot of carbon. And so that's really driving things. In soils, you're going to tend to have, 5 or less %. And so it's not going to drive things. And there's other sites in soils that could play a role. Also, we know in the unsaturated zone, we can get a lot of sorption to the air-water interface of PFAS. So additional attenuation. So I think I was going to show you this. This is a study that was done to reclaim land. So they were able to add 5 times the ag rate. And I'm showing you here on the left, the PFASs that we quantified, and it was a total of about 400 of what we quantified. Like I said, there's things that aren't being quantified and things that are not being extracted. And these were applied to these reclaimed soils. So not a very fertile soil, needed a lot of help. And so what we're showing here is concentration on the y-axis as a function of date. We're just now generating this data set, and this was some preliminary data we have. And so I think first, this gray area where we saw very high release showing up in the lysimeters at the 15 centimeter depth. I later realized that this was due to settling. It was a new established site. So this wasn't really our site. We are piggybacking on a site that was really just looking at carbon and nutrients. And so we wanted to look at PFAS. Then later with some of the heavy rain events, you did see occasional spikes, mostly of the 6-carbon carboxylic acid. And the short chains were also dominant in the, pretty dominant in the PFASs as well, in the product as well. Interestingly, what was in this pore water for this basically non-attenuated pore water was pretty similar to what we saw in our pore water assays, comparable. So we wanted to think about temporal trends. I mentioned that we were concerned if the difference between composted city waste and biosolids and short chain, long chain might have been timing of when they were collected. So we worked with the plant in Wisconsin that makes Milorganite, and we got additional years, 2016 and 2018. And it looked like definitely a huge decrease in long chain. That was the biggest contribution. So you see blue is the total and red is the long chain, and we see totals decreased, but we see most of that decrease came from the short chain. So that was encouraging and seemed to be logical and follow some of the phase outs that were happening. The differences are, could be due to variation in inputs though, not just, so that's part of the input variation, but also process. And we have to be mindful that we really only analyze the terminal acids in this project for this particular biosolid. So another biosolid that we got in 2019 that is commercially sold, Walmart, Home Depot, your common stores. And in this case, it did not decrease. So the acids that we only originally quantified went from 35 to 210. We analyzed additional PFASs in this study, but we hadn't quantified them yet. We didn't have standards running when I ran this at the time. And so some of the difference could be due to we've improved our extraction procedure, and that's another whole talk all on its own. But it's probably most likely related to sources coming into treatment plants and so we have to talk to this plant a little more, because they could be increasing their capacity. They could be taking in influence streams from other sources that they weren't back in 2014. So it's hard to say, but it is, I guess we, can say that we can't think that everything's just decreasing, and we still saw plenty of long chain acids in this product. So looking at some more biosolids we collected in 2019, I'm just showing you total range anywhere from, close to 200 to approaching 1,000 for the PFASs that are being quantified. And I actually haven't shown you guidelines yet, but I will. And then here's just 3 that Maine actually had started to try to regulate PFOA, PFOS, and PFBS in their biosolids. And as you can see with the Maine guidelines, none of the biosolids would have passed all 3 criteria to be able to be land applied. And so that's pretty restrictive. And the other thing that was interesting is, in spite of the different size, regional size, and the properties and the processes that were used to create these biosolids, there was really kind of a relatively narrow range for specific PFASs, so it's always within a 1 or 2 order of magnitude. And here's some more, max and mins that we saw across the board. So again, for the terminal acid metabolites, from some of the precursors that are really intermediates on the way to the terminal, and then some additional precursors that would have been parent to some of these other precursors. And so overall, what's interesting is the things that are not quantified typically made up to 50% of the total PFASs that were present in these biosolids. And that did range between 20 and 50%. And again, I want to remind us that we haven't actually extracted the larger precursors, or we weren't detecting them in our QTOF because we only go to 1250 for the mass range. So what are state reactions to PFAS? We have what you can see here. I've shown you for Michigan, Maine, and Vermont, California compared to Canada. And if you just take 15 seconds to look at this, you can see how much acceptable levels vary between different states and different countries. So it's really a moving target. And this is significant when we're talking about our waste challenge, because how you deal with your waste might be different in Michigan than in Maine and Vermont versus California. So it's really a challenge as to what we are going to do. And Canada is, not as far along as a lot of the states in the US, but they are, it's definitely on their mind. They're thinking about it. They're working on it. So here's the problem with the drinking water guidelines. They use those and then work backwards to say what's okay to have in soils, what's okay to have in soil amendments that we apply to the soils. And so here's 3 that I will show you for states. Alaska has proposed levels that are okay in soils of 1.7 ppb for PFOA, 3 ppb for PFOS. New York has a sum of the 2, 72 ppb. Maine, as I mentioned, they have right now defined 3 criteria for 3 PFAS that any of the land appliers, the programs that are applying biosolids, they have to test their biosolids and they have to meet this criteria. Well, it's kind of easy to meet New York's criteria most of the time, not all the time, but most of the time, especially if it's a non-heavily PFAS using industry impacted biosolid. But the main criteria, those pretty much can't be met by most biosolids and actually even a lot of our composted city wastes. So what about treatment levels? What do we do now that we have these biosolids? And we looked at a few treatment processes. We did not do the treatment process ourselves. We worked with facilities that use these treatment processes. They provide us the input and then the output from the process. And what we saw from this data, limited data, just 4 different plants, is that only blending decreased the PFAS loads. And that's primarily blending with a non-PFAS or low PFAS containing material. And that, led to dilution. And although there has been some evidence, encouraging evidence, that alkaline hydrothermal reactions can degrade PFAS in aqueous solutions. And most recently, I saw an article come out about aqueous film forming foams, that is not easily transferred to biosolids because of all the carbon and other things. Here's, I wanted to put this a little bit in perspective. So when you're applying a soil amendment, it has a different amount of nitrogen and different amount of PFAS loads. So what I'm trying to show you in this graph is, on the left, you're seeing the concentration of PFAS that would be applied, that is in the product, and that's the open bars. On the right, I have the axis of how much of the perfluoroalkyl acid you would be applying to the soil if you followed the nitrogen recommendation, and that's the red bar. And so clearly you can see, just looking at this, that because some materials, so material M has very low PFAS load, but it also has very low nitrogen. So you have to add so much that you actually add very high PFAS loads to the soil. And this is only looking at the alkyl acids. Whereas the Milorganite samples, they are very rich in nutrients, rich in nitrogen. You're not going to apply very much. And so you're actually going to apply a very low level of PFAS to your biosolids. And so honestly, even though engineers, we never want to say dilution is a solution, right now, that might be a very pragmatic management strategy to be using for right now, until we can get PFASs out of our wastes. I wanted to show you another treatment technology, especially since I worked with Dr. Wei Zhang at the Illinois Sustainable Technology Center, which I know was mentioned yesterday. He has a little system for pyrolyzing things. And so we wanted to see about if we pyrolyze biosolids, how does that change PFAS content and PFAS release from the material? And eventually on our EPA STAR project, we want to see if it seems like it does a good job, can it be mixed with biosolids to other biosolids that and help attenuate PFAS release. And so here is some data where it's important to show. I know a lot of commercial labs say, oh yeah, we analyzed that biochar, there was no PFAS in it. But if you only look at the biochar, the way it's applied, it's really hard to extract PFAS out of it. So if you grind it, you're going to see a lot more. And that's compared to, I'm showing you the Class A biosolid that originally had the PFAS in it. And it was a very, 1,000 parts per billion measurable acids in that biosolid. And you can see that you can get a concentration effect because you get a huge mass reduction when you pyrolyze. And then you also could get loss. Maybe there's some breakdown, not going to be a lot, I expect, at 350 degrees. Some might be volatilized, which means it's in the syngas. And so we have to deal with that. So it's not an easy thing to evaluate the overall effectiveness. And so then I wanted to show what happens when we do this pore water assay. So again, this one, just the acids alone were approaching 1,000 ppb prior to pyrolysis. And the pore water concentrations from that biosolid were anywhere from 6 to 1,200 parts per trillion for individual PFAAs. Once it was pyrolyzed, yes, we got mass reduction. Yes, we got concentration of some things, but in terms of release, that the PFASs did not want to release from that biochar matrix, and that's a good sign. And the only thing we actually saw were carboxylic acids, and all well below anybody's levels of concern when you compare them to some of the drinking water guidelines that I showed you. Another thing is people are incinerating, but that's a big problem. I'm really concerned about that. And now there is some funded research out there looking at what happens when we incinerate. Our incinerators aren't really designed to mineralize PFAS in waste or in our spent consumer products, our carpets, our clothing, and the list goes on. In fact, just recently, 2 companies in Indiana are now facing suits for incineration of military AFFF stockpiles. People are very upset because they don't believe we have a way to evaluate this yet. And now some states actually have bans on allowing any incineration of PFAS containing materials. So that's not an easy answer. So I often get asked by reporters, well, given that these PFASs are forever, and shouldn't we just ban all PFAS containing materials from being land applied or being discharged to streams? Okay, that means, all wastewater effluent can't go anywhere. What do we do with it? That means all the biosolids can't go anywhere. What do we do with it? And so that really puts a very heavy burden on public municipalities. And we could go into how much inequality and disparity would be faced by the people that have to pay for the taxes, but that's another talk also. And it leads to a lot of unintended consequences. So we need to be careful and not be overly conservative about this. We've been living with them in our home, our cars, our offices, in the environment for a few decades now. Let's just be a little patient about how we decide to go about actually regulating. So in between, what we need to do is control sources coming into our biosolids and into our plants. Pre-treatment is the perfect thing. We did that for metals. When EPA had a ruling about metals in industry that were bringing in too high metal loads into wastewater treatment plants, they had to pre-treat. Very easy solution. We don't have metal problems now in our biosolids. Michigan has been very proactive and has started identifying and controlling sources coming into their plant, and it's enabled them to meet their criteria. For example, 11 or 12 parts per trillion PFAS discharge in effluent. These things are being met because they're controlling what's coming into the plant. They've also learned in that process that just because you have 6 chrome platers that might use PFAS or 7, it doesn't mean that they're all contributing high loads. And in fact, in their case, they only found one plant that they said, you need to pre-treat. The other ones were okay. We need to regulate non-essential uses, and you as a consumer can play a role in that in this age of digital age. And you can choose what you buy and try to buy things that don't have PFAS. Let's drive the innovation. And that'll go a long way to reducing PFAS coming into our municipal waste facilities. So I say move slow on regulation, move fast to regulate and ban things coming into our products so that we get them out of our waste stream. And let's be a little slow in regulating so that we don't cause a lot of unintended consequences and heavy burdens on people that can't handle it. And so together that will make us a winner. But I'm not going to end here. I want to end with a few more things so you know what's going on. So PFAS containing food packaging in the state of Washington, they've now have things in place, and it was partially driven by our data that we collected with Zero Waste Washington. It's important for you to realize that it's easy to say ban, but they have to find a safer alternative. And this is across the board. So it has to be evaluated for hazard and exposure. Is it practicable? Is it economically comparable in cost? Can it fit in the production line that is already used? Does it perform as well as PFAS? So a lot of things that they have to think about. State of Washington also has bans on firefighting foam training with the PFAS foams, and they have firefighting sales ban that's going to happen. They've instituted it, but it hasn't happened yet. And then for everything, and then personal care equipment that people have to know if they contain a lot of PFAS. I'm not actually worried about their PPE equipment, but that's another talk. State of California, they've now got PFAS containing products as priority products for carpets, textiles, leathers, and working on food packaging now. So what's our current path forward? And I'm going to close with this. We got to continue research. There's so much increasing amounts of research being done, including treatment technologies and alternatives. Meanwhile, we ought to consider blending for our biosolids. I'm working with some of the biosolid applicators in Indiana to do that. We need to control sources, big thing, pre-treatment. We need to regulate and ban non-essential uses. And the last two things are going to go a long way to keeping these out of our products and out of our waste stream and reduce our exposure. So with that, lots of people played a role in contributing to the data for the talk, and a lot of different funding agencies. We've been working on this for about 15 years. So if we have time for questions, how'd I do?
Thank you, Dr. Lee, for an excellent presentation on PFAS. And we do have time for questions. So Sarah, whenever you're ready.
Yeah, we did have one question coming in kind of early in the talk.
You're hard to hear all of a sudden.
How about now? How about if I actually put my microphone near my mouth?
Much better.
A question came in early in the presentation that said, in the example you showed of 8-2 FTOH degradation to PFOA, it goes from 8 perfluorinated carbon in 8-2 FTOH to 7 perfluorinated carbon in PFOA. Does this imply that microbes attack a carbon-carbon bond within the perfluoroalkyl chain? And if so, any idea why that happens? I would generally expect microbes to attack bonds outside the perfluoroalkyl chain.
Yeah, that's really interesting because you don't just see PFOA, you will see shorter chain acids formed as well. But then it stops. It doesn't actually take them any further. And a lot of people, are trying to explore that to see if they can optimize, creating microbes. And I know, Peter Jaffe's group is, showed, what they think is some success. I'm not sure yet. But it is a very interesting dynamic that happens. And it does start by, attacking the carbon closest to where that ethyl linkage is. And so you can look at some of Wang's papers from DuPont. He's talked about that some, but we have not, been able to optimize, grabbing those microbes to see if they can do further. I mean, there are there's different things that people have seen in pure cultures where they maybe can get the, sulfur grabbed out of PFAS, which will do an initial breakdown, but then it doesn't really go any further. And it has to do with that telomere linkage, because electrochemically derived compounds will only end up producing, like PFAS. If it's got 8, it's just going to go to PFAS. That's it. So it's kind of interesting. It's a really good question. We have been wrestling with it for, a decade plus.
Great, thank you. The next question is, some of us are not scientists and are here today as impacted community members. If one lives near agricultural fields with land spread biosolids with known high concentrations of PFAS, what is the most important data for us to ask for or have, setting well testing aside? Is having TOP assay or PIGGY data for soil?
I mean, any data could be useful, but then it's just how do you translate that in terms of your impact? I just last fall, there was 3 national priority grants awarded for looking in well water to specifically answer the question about PFAS and biosolids in agricultural operations and how it might be impacting well water quality. And so I think in the next couple of years, we'll have more information. The problem is if you see a certain fluorine content and it doesn't translate directly to what's going to show up in the pore water, what's going to leach and be in your groundwater. Because a lot of these precursors, especially the ones we're not even tracking, I didn't show any data from Lecter's group in Canada, but they actually looked at some biosolids and sediments from these fields that had received a lot of 3M, well, it was biosolids that had a lot of 3M PFAS in them. And they found that the things that you normally would quantify and even extract, they had to extract whole new ways, were much higher than anything that we quantify. However, and this is something that my lab is looking at, we don't know how fast they degrade. And I would speculate that they degrade very slowly such that they might not cause any major blips of PFAS showing up in your groundwater. And so, you have, so I guess, it's hard to answer your question directly, but I would say, don't be overly concerned, but definitely query and ask for quantitation. But I think, you have that right to be asking for that. So, and when you say it's heavily impacted by PFAS, there's a whole range of a thermometer for what's heavily impacted and what's going to lead. So it depends on how close is your water source to the soil, what's your soil type, what's your climate like. So it's not an easy question. But I think in the next 3 years, we're going to have a lot more answers to some of those questions. Doesn't help you right now, but.
Thank you. Looks like for now, that's all the questions we have that have come through. If anybody else has questions, oh, here we go. One more. How do you see the interplay between broad-based methods such as non-targeted analysis and TOP assay and regulatory work, which typically relies on targeted analysis methods with set analyte lists? And then as a follow-up, what should the regulatory community be taking from work that shows that targeted analyte lists are only turning up small percentages of total PFAS?
Yeah, that's a good question. I will say that I think that what shows up in the water outside of an aqueous film forming foam impacted water supply is a pretty small set of PFAS that are actually, mobile enough and showing up in the water. I think the big problem is when you're looking at what's in our soils and biosolids, that's where you might have a bigger issue. EPA is expanding their watch list, and the PFAS that they're quantifying are now, 24, and they might go up a little more. So it is something we have to be mindful of. Originally we were only looking for PFOS and PFOA, and still the majority of the data out there is just on those 2 PFAS, and that was just a tip of the iceberg. So we've gotten a little further down in the iceberg, but we're not there. But I would say what's in water is going to be a very limited subset because they have to be mobile enough to end up there. But yeah, I do know, I just listened to a talk from the Great Lakes, not yesterday, an earlier talk, not a conference, but they had really highlighted that for their fish advisories, most things are still related to mercury and PCBs, interesting enough, not PFAS, even though, you know, they're on the watch for PFAS. So PFAS isn't our only contaminant of concern that we're having to deal with, but it definitely is getting a lot of attention now.
We have time for one additional question.
Okay, I have one more then. Someone is asking what your opinion is on regulating PFAS as a class.
I'm pretty supportive in general of that, but how we define that class will be important because if we just say it has a CF3 group, that doesn't work for two reasons. Manufacturers have gotten very creative and make them without a CF3 group. And also there's pharmaceuticals and pesticides that have CF3 groups in it because just because it has a CF3 group doesn't make it a PFAS. So depending on how we define it, I think the biggest problem is this non-essential use. And although I was surprised to find, like even Washington, there was a few, like 3 or 4 packaging materials, they say they can't find comparable alternative uses. So they're still allowed to have PFASs in them. Believe it or not, it's your French fry containing carton that you get. It's the clamshells that we, you know, have take home in. So that surprises me. But outside of that, I think the biggest concern is where it's saved lives in terms of in the medical world, you get a heart valve put in that's Teflon. So Teflon is not going to degrade and create all these things that we're seeing in water. It is very persistent. However, to create it, you need to use PFAS that we do worry about. And so how confident can we be that you can create Teflon and a lot of the products that are critical in the medical world without causing, a lot of environmental contamination? So that's a concern. But honestly, our biggest problem, the reason PFAS is so widespread is because of repeated use of AFFF for several, for 3 to 4 decades, even though back in the early 80s, Jennifer Field from Oregon State found them in the groundwater under an Air Force training site when she was working on chlorinated solvents. But everybody just, we need a more open, transparent system to be able to report things like that to EPA. And nobody was collecting foams. You use them, you train with them, you put out a fire, they just go everywhere. And the second thing was direct discharge by industry. And it is frustrating that even after there was phase out of PFOA, direct discharge, PFOS, then we turn around and had Chemours do direct discharge of something that wasn't on the list, Gen X, which, now it's on the list. That's frustrating. But I think if we can control, when all those things are brought to perspective, the rest of the PFAS that we're exposed to probably is pretty low and we wouldn't have these huge problems. So, yes, we have landfill leachate we have to deal with and some of the solid waste that were buried, like, what's happened with Wolverine and Michigan, aquifers. But if we managed our chemicals well and actually learn from our mistakes, which we seem to be very slow to do, I don't think we would even be having as many problems as we have now. Because they do give us a lot of quality of life. That's what, pharmaceuticals, the whole suite of them that are being talked about during this conference. And it's just, how are we managing them? How are we managing our waste? So yeah, good question.
I think that's an
You guys
excellent
ask
point.
hard questions.
Thank you, Dr. Lee, for an excellent presentation and discussion on PFAS.